Okay, this is lecture number 6. Let me just give you a quick recap of what we were doing. So, this is a simple model of the PLL with a phase detector followed by loop filter with a transfer function f of s, and this at the output of this we are having VCO, and this is where we all started. The input is voltage signal V in, the output is voltage signal V out, but what we were interested in is the phase input and phase output. Okay, this is a simple PLL model which we have been looking last 2 or 3 days. Here we consider different cases, so let me just take one by one. Case 1, we had f of s is equals to 1 by 1 plus s by omega p. Everyone remembers it, right? This is where we all started, and this can be realized by using a simple RC filter. Okay, phase detector is a mixer based phase error detector here, so let me just make this, if you have forgotten, this is the phase error detector which we were using. The output of the phase error detector is voltage VE. The output of the loop filter is control voltage for the VCO, which is VC. Okay, now we found the problem with this kind of filter, that if we had any frequency error between the input and the output. So let me start afresh telling you that, let's say the omega input frequency is omega n. Okay, input frequency is omega n, and output frequency I write it as omega out. This is output frequency, and omega out is equals to omega free plus 2 pi times kVCO times VC. Okay, set it up. So if at time instant t equals to 0, your VC was 0, so omega n minus omega out is equals to omega n minus omega free, delta of omega. Okay, so the problem started when this delta omega is greater than a certain value for this loop filter. Okay, and what we found, that if delta omega is less than is greater than 2 pi kVCO kPd, in this case the PLL cannot lock to the zero frequency error. Zero frequency error means omega out at limit t tends to infinity, omega out should be equals to omega n. This should be the case, right? But because of a large frequency error in the beginning, delta of omega, it cannot lock to a zero frequency error. That's the problem which we have. Okay, and the way we thought that we overcame this problem was that we introduced an integrator where we said let f of s is equals to 1 over s, where this is an integrator. So for this, why did we choose an integrator? Because we found that with the mixer based phase error detector, the waveform, the voltage error which we are getting, that is somewhat asymmetric. So let me, this V error was having an asymmetric waveform. So this is what it was having for a mixer based phase error detector. So we thought it has some particular DC voltage which is a representative of the frequency error, and if we can amplify this particular DC voltage by a large amount, actually by an infinite amount, then we can recover the frequency error. Effectively what we were doing, we were actually by using f of s equals to 1 over s, we were making that k 2 pi, this is f of 0 here, 2 pi k VCO k PD times f of 0 tends to infinity. This is what we were trying to do. Okay. But the problem which we found, that if we were just using a simple integrator, we did not have this waveform at all. Means whatever the waveform we were getting means so if we just use a simple integrator, we did not have this waveform, and the integrated value of whatever the waveform we were getting at V error, that was close to 0. Okay, that is why we told that okay, we need both the things, the proportional and the integral path. Where we considered case 3, where f of s is equals to 1 over tau I into, so let me just write it here itself, 1 by s plus tau p over tau I as a constant. Okay, so this filter means I can just write this filter in the block domain as tau p over tau I, and this one as 1 by tau is. I sum both these values and give this to the VC. Okay, this is VC proportional and this is VC integral. Okay. Now, in a steady state, or when I compensate for all the frequency error, so let me tell you. So let us say we had some frequency error to begin with. Delta of omega is the initial frequency error, right? So if we want to compensate this frequency error using the control voltage, I should have 2 pi k VCO times VC should be equals to delta of omega, whatever my initial frequency error in a steady state, right? Which is equal to 2 pi k VCO times VC has two values, VC proportional plus VC of integral. Okay. Now the integral path has an infinite gain at DC. Okay, so integral path can in the steady state it can have a 0 at the input, but it can still have some finite value at the output, right? So this value itself means this can be equals to 0 in a steady state, and this can have some finite non-zero value, such that delta omega is equals to 2 pi k VCO times VC of integral. Okay, so for this case, what is the error at the input? V error when this is satisfied. What is the error in a steady state? 0. So if V error is equals to 0, what is my VC proportional? 0, right? So this answers your question that the plots which I have showed you, where the proportional control voltage was changing initially but finally settles to 0, and the integral control voltage finally settles to some value such that it compensates for the frequency error. Pardon? Case 2, you did not have any asymmetric waveform to start with to amplify. Means you can, I did all the maths last time, you can go back and do that you will not have the DC voltage to start. So you do not have, that voltage is called as initially as a pull-in voltage, so you start with a 0 pull-in, so you cannot amplify by any value. It's like 0 multiplying with some value. It's called as a pull-in voltage, whatever the DC value is. Right, but that keeps on changing because it's all in a negative feedback. Okay, so yes.
you are getting curve like this. For the attacks the recipient deals. So practically we are getting that extra one. So that is the pull-in voltage.
No, that is not the pull-in voltage as such. Pull-in voltage, the way we defined that was for when you started with all this PLL at time instant t equals to 0, there will be certain error at the output, right? And means the feedback has not yet kicked, means not that effective, the values are still low, right? So it has some DC voltage. So that starting voltage at that given instant of time is the pull-in voltage. It does not have any much importance there. Okay. Means it does not have any such importance that you need to see, because this voltage keeps on changing depending on the frequency error. Okay. So this is all the locking in PLL, means frequency locking in PLL across with 3 different cases which I have shown you. Okay. And this has nothing to do, I mean this was a question at the end of the last class, this has nothing to do the definitions of lock-in range, pull-in range and hold-in range. Means I define all these frequency ranges one by one based on how the PLL progressed. But these definitions of the frequency ranges is independent of the PLLs which we have learned. Okay? Means I can apply, I will ask a question, what is the pull-in range, what is the hold-in range, what is the lock-in range for any kind of PLL. Okay? So don't think that if after the case 1 I introduce lock-in range, oh, lock-in range is defined for this PLL. No. Lock-in range is defined for all kind of PLLs. So is the pull-in range, so is the hold-in range. Okay. So let me reiterate about the definitions of these ranges. This is they come under the frequency range. That how do you define what are the different kind of frequency ranges the PLL can have. So let me just give you a brief background. So let us say I have this omega in as an input and omega out as an output frequency. Okay. Now this particular PLL is locked at time instant t equals to 0. Omega out was equals to omega in, which means that my delta omega was equals to 0. Okay. So now the question is, if I change my omega in by a small amount, see absolute frequencies are this. Okay, I do not care about right now absolute frequencies. If I change my omega in by delta omega, if omega in becomes, let me write this as omega naught, so it becomes a little easier. Omega naught plus delta omega, what happens to omega out? Okay, ideally this should lead to omega out equals to omega naught plus delta omega. Ideally this should happen. Okay, but whether this will happen, how it will happen, that will define that how much delta omega I can have as a lock-in range, as a pull-in range, or as a hold-in range. Okay, so let me make this plot and say I am plotting delta omega here. Okay, delta omega at the input, which is equals to, let me do not write like this. So let us say this is omega in and this is omega out at t equals to 0, or at a starting point. This is my starting point. Okay, don't read this as omega 0 value. This I am just saying at this point omega in is equals to omega out. I want to give you the whole large scale and small scale, both the pictures at the same time. So at this center point omega in is equals to omega out equals to omega naught. Okay, now I change my omega in by a delta omega value. So ideally my omega out should also becomes the same omega in. as I keep on changing my omega out, omega in, my omega out should keep on changing and tracking this path, positive or negative direction either. This is what should happen ideally. Okay, now let me define. Lock-in range is defined as the range of frequencies, means range of frequencies, which is delta omega here. Okay, don't get confused with this delta omega as omega in or omega out standalone. It's a delta omega once you have locked it. Okay, the range of frequencies to which the PLL will lock without cycle slipping. Without cycle slipping. Okay. That means without cycle slipping is equivalent to without increasing the phase error more than 2 pi. Okay. And once the PLL locks, this equation means whatever your delta omega should be equals to 2 pi kVc over Vc in steady state. In a steady state, there's means if the PLL locks to the any given frequency error, there is no means any given change in the frequency, there will be no frequency error. Okay, and even the phase error will not be changing with respect to time. That's the locking condition. Okay, now pull-in range is defined. Range of frequencies. Yes. Cycle slipping. Once you cross 2 pi, it is a cycle slipping. Okay. So range of frequencies which PLL locks with cycle slipping, means this is the maximum range of frequency which PLL can lock in. Okay, this is like lock in and pull in range, and the lock in of the PLL is confusing here. The range of the frequencies which the PLL can acquire with cycle slipping, that is that all that frequencies comes under pull in range. And this is where I made a difference, means if you remember, I introduced this lock-in range for the case 1 PLL where Fs was a low pass transfer function with the DC gain 1. Okay, and I told that okay, if the frequency error is larger than this, you will not be able to lock in. Then I brought in the integrator and I said integrator and a proportional path, that okay, you can lock into this frequencies also with the f of 0 tends to infinity, right? This is what I introduced. And then I also showed you some example where you can see where the frequency error was large, so it was cycle slipping also, right? That concept I introduced after introducing the integrator and the proportional path both. So pull-in range actually is, means this is just an example. If this is delta omega of L, defined as delta omega L, this one is delta omega P, and this is delta omega H. Okay, so if I keep on increasing the frequency such that I am still able to lock in, but with after cycle slipping, all that frequencies will come under delta omega pull. Okay. Now, after the pull-in, what happens? So let us say my PLL is locked to pull-in. Okay. For an example, let me start with some number. Omega in equals to omega out is equals to 1 gigahertz. Delta omega of L is equals to 50 megahertz. Okay, and for example, I can say, let's say delta omega of pull-in is equals to 200 megahertz. Okay, one thing here, that if you are having a loop filter with an ideal integrator like this, then the pull-in range is infinity. If you remember, for this particular thing, I defined that delta omega p is less than equals to k times 2k dc by k minus 1, where k dc was equal to 2 pi kpd kvco into f of 0, okay, and k is equals to 2 pi kpd kdc, sorry, kpd kvco times f of infinity. So if f of 0 is equals to infinity, then the pull-in range is infinite. No problem there. But you may not be able to implement an ideal integrator. That's why it will have some DC gain at the integrator at the frequency equals to 0. That's why the pull-in range will become limited. Okay. But let us say it is locked and omega p is equals to 200 megahertz. So what happens when you are at this particular point? PLL is locked, omega in is equals to omega out, phase error is also equals to 0. Okay. Now if I give a small step at the input, this step can be as small as possible. Okay. What do you expect from the PLL to do? It should lock, right? Ideally, right? So you can keep on giving such small steps and increasing the frequency or increasing the output frequency of the PLL by changing the input frequency of the PLL. Okay? And at some point what happens, this point can be as close as very next to the pull-in range also. It's not that it should always be some delta away, it can be next point also. Right? So at some point what happens, if you give any value more than, means any delta omega larger than at some frequency value, the PLL just drops, means it loses the lock. Okay? And so it loses the log, and that frequency range is called, means this value will be called as delta omega s h, hold-in range. Okay. If means you make a step forward, if you take 2 steps back in the frequency and you think the PLL will lock, it will not lock. Okay. See, if the PLL could lock on its, if the PLL look at this way, the PLL is not locked, is free, the voltages are, no, we do not know where are they, right? And then whatever the frequency error you are, whatever omega in you have, omega out, at the best you can say omega out will be equal to omega free, right? So the frequency step is quite large, and the large scale dynamics are not able to bring the frequency back. Okay, if they were able to bring that frequency back, means if this point, see what I said to you was, if you go beyond this point, the PLL loses log, right? If I want to trace it back, I gave the input here, this is the omega input I gave, but the PLL was running free, with the free running frequency. So the actual step to the frequency is not this, actual step is this much. Agree? So if this is the large frequency step, then the PLL should, like whatever it, PLL should do all the large scale processing of the whatever signals, and then it should get back that voltage. Okay, with cycle slipping, without cycle slipping, you don't care.
When we are locked at the pull-in range, frequency when we are increasing slowly, so that is using small signal or
that can be through small signal also. Means you take, see if the PLL is locked, it is on a stable condition. If you make it, everything is like an incremental circuit. So if you make a small change, the output should also
gets locked. That's new frequency. After that, you have to increase.
Yeah, increase. This is the process in which you can find the hold and range.
Lock condition is something like some bias to
lock condition is see means if you pick any arbitrary point, you pick this point, and you say the PLL is locked at this point. What is the condition for PLL locking? Omega in equals omega out. Okay? And if you are using the second case where you are having an integrator thing, right? At that time, V error is equals to 0. So V error is also equals to 0. Okay? And VC will be equals to whatever the delta omega divided by 2 pi k VCO. This is VC. So this is a stable, all the delta means all the voltages, all the phasors, all steady. No change ideal. Okay, now if I give a small disturbance here, the disturbance is so small that you can treat all the signals right now as all the blocks as a linear blocks with the linear gain. You can treat it. Okay, then if you change the input, small input, the output should also change proportional. Right? We will apply all this kind of Laplace transform once the PLL is locked. If we give any small disturbance, we treat the system as linear. And we apply all the linear transfer functions on that block.
Once it is locked, we are next step. So it is locked, that frequency.
It should lock.
It should lock.
Yeah.
After that, we have to increase that.
No, so when you see, once it is locked, you slide a small step. The output also changed by that small step. Okay, and the new means this is VC, and this will change to new delta omega. It will get a new control voltage, and that new control voltage will become the new steady state point. Do not think that, okay, that's why I am saying you give a small step and wait for a long time such that it settles. The operating point is changing all the time. Operating point does not remain the same. Yeah. Here the operating point will keep on changing. Huh? I can't say that. Means it should be linearly, but it will keep on changing. It will not remain the same. So what is means? Let me just give you a basic thing. Let's say I think everyone has looked at this I versus VGS curve, right? For a MOSFET, and if we are at this particular point, we linearize here, right? But if we move from this particular point to another point here, I am just saying that the step is so small that you can consider all the linear analysis and you move to the next point. You should not be, means if you want to do it accurately, you should linearize the system at the next point. Right? So it will keep on doing this to a certain extent. After a point, when you reach the hold-in range, if you give any step further, breaks off. Right? And if you think that, okay, if the PLL has broken off, we control voltage, means it's like what loop it is operating, we do not know right now. It becomes like a, that's why I said, if I took one step forward and the loop breaks, and if I then at the input I said, okay, I took one step forward, the loop has broken, now let me take a 2 step back, so the loop should start working. It will not be like that. Then it is equivalent to giving this delta large delta. Okay? And this frequency, and we know that beyond this omega p, right? If we give this omega, any frequency beyond this, the loop cannot, means a large step, the loop cannot get that voltages. Okay? One other point which I will tell you, this is actually related to the hold-in and pull-in specifically. So, here, just a minute. Here I have told you that you can keep on taking small steps and you keep on approach the frequency omega h. Another thing is, if in place of going small steps, every time I take a step, after that I reset to 0, let us say. So, for example, let us say your delta omega L is equals to 10 times some delta omega 1. Okay? This is an example. Delta omega p is equals to some 50 times delta omega 1, and delta omega h is equals to some 70 times delta omega 1. I have just given you the range. right? If I want to trace this with respect to my omega in and omega out, I will have 10 and 70. Okay, this is what I am going to have, right? So now this is 10 delta omega 1, 50 times delta omega 1 and 70 times delta omega 1. This is what I have. So I told you when we try to keep on increasing, we can go up to the hold-in value, and after that it breaks off. Okay. Now another thing I will add on this, till your pull-in value, whatever the pull-in value is, okay, whether I approach 50 delta omega 1 from 49 delta omega 1, or I directly gave a 50 delta omega 1, the PLL will be able to pull in till the pull-in frequency. So what am I saying? That at t equals to 0 means, or t equals to 0, let us say omega in equals to omega out. I am giving you two cases. At t equals to t1, so my omega in changes from omega 0 plus 49 delta omega 1 to omega naught plus 50 delta omega 1. This is one case. Okay, or means the another case one is this, and another case is at t equals to t1, I make omega in go from omega naught to directly omega naught plus 50 delta omega 1. So in one case I take a small signal step of delta omega 1, in another case I am taking a large step of 50 delta omega 1. If this 50 delta omega 1, whatever the final frequency from this delta omega, if this is less than, means this 50 delta omega 1 is less than pull-in range of the PLL, it will lock. The only difference will be when you go from 49 to 50, you can approximate your small signal analysis. If you are going from directly 0 to 50, then it will be a large scale, large signal processing of the signal. Huh? Delta omega is independent, means if you do not have any limitations on the VCO, charge pump, mixers, it is independent of omega now. Okay.
So in case of this, there is no benefit.
Huh?
In case of there will be no benefit.
In case 1, when you have, means you are taking a step only of delta omega 1 there, right? But this is different from the free running. Okay, means then it's like you are already having a voltage of with respect to 49 delta omega 1. Okay, but for this 50 or delta omega 1, you will have a cycle slipping. Okay, so normally when we look at this pull-in range and hold-in range, we do not generally use these small steps. And I will tell you why I use the small steps here, because here I say that if I give a frequency error less than pull-in range, like this large step, the PLL is able to acquire the voltages and all. But if I give any frequency larger than, if delta omega step is larger than delta omega peak, PLL will not be able to lock in. Okay? But if you moved, if from here, means if you come to this pull-in range and you gave a small step and the PLL locks to that, that frequency comes under hold-in range. Okay, it is confusing, so that's why I am trying to breaking it part by part, that what is the difference between the pull-in and hold-in, how can we even simulate our PLL for the hold-in range. Okay. So let me repeat. So I have taken an example where delta omega lock-in is 10 omega p is 50, omega h is, sorry, this is omega h is 70 delta omega n. So when I say lock-in range is delta omega 1, you gave any frequency step between 0 to 10 delta omega 1, your PLL is going to lock without any cycle slipping. The only thing is you cannot approximate the PLL with a small signal because the step is large. Okay? If you give a frequency more than 10 delta omega 1, okay, and less than 50 delta omega 1, any frequency step, the PLL will lock but after cycle slipping. If you give any step larger than 50 delta omega 1, directly, step larger than 50 delta omega 1, the PLL will not lock. But if you give a small increment at 50 delta omega 1, right, you may keep on increasing the frequency with this, all the small signal means it will happen in the actual PLL, it's not that the mathematical, it will happen. I will tell you why also. You can keep on increasing the frequency, but after a certain frequency the PLL will lose the lock. And if you want to come back by giving any extra 2 steps back, it is actually not 2 steps back, it is actually a frequency which is more than the pull-in range, so PLL cannot pull in at all. You have to come back at this point which is within the pull-in range of the PLL. Okay? Now the question should arise, why at the, when I give a step of 50 delta omega 1, the PLL is able to pull in, but if I give 50.1 delta omega 1, 50.51 delta omega 1, the PLL is not able to pull in, right, as a direct step, but when I give a small step, it is able to lock. Huh? No, it's locked already, but it should acquire, see, giving an input step delta omega as 50.1 delta omega 1, okay, or once locked at 50 delta omega 1 and giving a step of 0.1 or even I would say 0.00 something, so 50.001 delta omega 1, right, these are two different in the dynamics of the PL. Okay, yes.
So let us say initially data is equal to omega, and take a step of delta omega.
Yeah.
I wait for infinite time, and again I give a step of yeah. Will it again not?
Huh? If you give a very small step such that it does not.
So what I'm saying is, after I give the first step, I wait for infinite times. So I call that as my new omega naught. And then I again give a step of delta omega.
No, but so the one thing is there.
So omega
No, I will say the difference is this, that the delta omega which you have got, right, means the new omega which you are defining, that new omega is not defined with the control voltage of 0, with a phase error of 0 or something, right? And all this thing is for a loop gain where f of 0 is not infinity. If f of 0 is infinity, it's an infinite pull-in range. Okay, so that VC is there, which is changing your operating point. Okay, so the question which I just asked before, that what happens, why it is able to lock in after some, if you give a small step, but if you give that large step, why it does not. Okay, so let me come back to this PLL block diagram where you have V error, VC are the two control outputs, and with respect to this VC there will be some phase error at the input, whatever the VE is, right? And if this loop filter is not having an infinite DC gain, then this phase error will not be 0. It is 0 only because it has an infinite DC gain, right? So what happens is that when you, let's say when you are at the pull-in, exactly at the pull-in point, and you give a small disturbance, right, the PLL can operate and get that extra voltage without limiting any of this phase error detector or VC or something. Okay, it's not, mostly here it's the phase error detector. Okay, phase error detector output will not get limited because it's a small change, and once it has saturated to a certain point, right, it will break off, even for the pull-in, right. Now, when we give a large step at the input, so let's just start doing one simple thing. So let us say, so I have phase error, V error and VC. These are the three voltages which I have, right, and means for a given frequency error which I am talking about, delta of omega. Okay. For example, let us say the V error is close to 0.49 something. This is half of sine of whatever value it is. With respect to this, I will have, means you can write the phase error as a sine inverse of this with the gain, right? And you will have a control voltage in the steady state, tau p over tau I times the whatever the control voltage you have, plus whatever the integrated value you are having. Now, when I change from one particular delta, when I change from 50 delta omega 1 to 50.001 delta omega 1, this value needs to be see. VC can also change here, let us VC1. This value can also change when you come to next control voltage, and even the phase error can change. Agree? The final thing what matters is, so your VC is equals to VC proportional plus VC integral, okay, and this is equals to tau p over, means I should not write, this is becomes an ideal integrator, so tau p over tau I times V error, okay, and the integrate, whatever the gain of the integrator at that particular point, you will have corresponding integrated value. Okay, this is not an ideal integrator. How can you realize an non-ideal integrator? Means you can say I am having this capacitor with a finite gain A. This is a non-ideal integrator. So the transfer function of this is going to be some of this loop filter will be like this. Very large gain, but it's still not infinite. Okay. Now look at it. If I give any change in the frequency error, my V error can change and my VC integral can also change, right? But if my phase error has saturated, it is at 0.5 something, right? Then my V integral can't change at all. So this is all the dynamics which will, this is all the loop dynamics, so it cannot change. That is why if you give a large step, it may turn that phase error is also saturated, and that's why my V control for the VSO is not varying and I am not able to lock in. But if I give a small step itself, then the phase error may not saturate and the feedback part works to bring the integral part to desired value. Okay, this is a little bit on a thought process. When you try to do it in simulation, you will observe this.
Phase error saturates to properties of mixer.
Yeah, phase error is a mixer. So all this thing, whichever I am talking, this is with respect to this means the pull-in range, lock-in range, whatever we will define. We are defining for one particular type of PLL, and you can define for other also. It will change with depending on what phase error detector and loop filter you are going to use. Okay. Phase error saturates means if the phase error becomes, let's say, pi by 2. So it is giving you the phase error detector is giving you the maximum value or the minimum value, right? But whatever it gets saturated to one side, and the proportion and the integral path is trying to recover the frequency, but it is not able to recover the frequency. Okay. It can appear cycle swapping. There will be. Okay. So after pull-in range, actually, if you means, that's why I'm coming back again. After pull-in range, if you give any frequency step which you give larger than the pull-in range, you will not actually lock at all. Means if the step becomes, means if the frequency step which you give is 51 delta omega 1, PLL will not lock. Okay, because it is not able to acquire these state variables. Let me just get it a little more mathematical. These are all the different state values: control voltage, error voltage, phase error. It should, in order to lock, it should have one solution only exists. Okay, but if one of the blocks is getting saturated, it is not allowing the loop to work, then it will not lock at all. It's like making the loop dysfunctional. Okay, this will appear only when you can feel it better when you only simulate this. Yes. That is where I pointed out. It's not, once it is locked to some frequency error, you give a small step, right? But what is your control voltage at that point? It is dependent on this free running frequency and omega input, right? Even the control voltage is dependent on that, error voltage is dependent on that. So all these values of the different blocks depend on what is the actual frequency error with respect to the free running frequency. Okay, it is not like completely independent. Okay, and when you try to do a small signal analysis, you will do at that particular operating point. You cannot do at omega with respect to omega free. If you give a very small step, see, it is locked. If the lock is stable, if you give a small step, it may be able to again keep that. It means it will be able to acquire that control voltage.
So that is for
okay, so let me make it clear. This is omega in equals to omega out equals to omega naught at this point, right? After this, whatever value I am changing at omega input, this is with respect to omega input. So I am defining the range with respect to my omega free value as such, you can say. Okay, this is with respect to that I am defining. No, I am saying, see, at omega pull in, you give a small step to omega in. So omega in has already become omega naught plus 50 omega 1 in the example, right? No, I am saying that you cannot call that as a new omega naught because your control voltage, your phase error, your V error are not the same. They have acquired some value depending on the difference between the free running frequency of the oscillator and the input frequency. So you cannot call that as the same and cannot use the same operating point. What? No, means this is your application, right? It's not. Means we want to change omega in, your omega out should change. That's what ideally you want. Your PLL should track the input frequency directly or in multiple. Okay. So coming back to this PLL block diagram, I said that after omega pull in, if you give, I mean, if the frequency step is larger than omega pull in, it is not able to acquire the required control voltage, error voltage, or the phase error. But at the verge of the omega pull in, if you give a small step, it is able to acquire slowly. You need to give time to it, right? So now the question, see, one way to simulate for the hold in range is the way I have told you. Okay. Now there is another way to simulate for this hold in range. Let us say, so let me back calculate everything. Let us say the delta omega which I am going to give is equals to 60 delta omega 1, for example, right? Means I am locked at omega naught equals to omega in equals to omega out equals to delta omega naught, and I give a step of 60 delta omega 1. And I know that if I lock my PLL should lock to a control voltage which is equals to 60 delta omega 1 by 2 pi kVco. This is my control voltage, right? If it locks, it should lock to this only. There is nothing which is there. If this is my VC, I should calculate what should be my V error. Okay, I can calculate back because this my transfer function is also in DC. I can calculate what the DC value of the phase error should be. So I gave that particular V error value. Means I am first calculating, and then with respect to the V error, I can also give my phase error. So I know if it locks, it should lock to these values in a steady state. Okay, what do I do? Then I start my PLL. So this is FS, a mixer based phase error detector, and this VCO, right? VC, VE, and phase error here. So when I change, give a delta omega here as equals to 60 delta omega 1, right? At the same time, I give a phase error offset in the sine wave. This is for simulation purpose. Okay, this is not what will happen in a real PLL. You cannot change it directly. For simulation purpose, I will give this phase error at the time instant, the time when I give delta omega 60 delta omega 1. At the same time, I will give that V also. I will just directly, I will put that value as a V, whatever I calculate from here. Okay, and similarly VC, right? And observe the and run this PLL in a transient time domain. Means all the equations should follow. It is in a feedback loop, so everything should work as per the feedback loop. Okay. So now I will see whether this V error, what happens to V error, VC, and phase error. See, this is like the starting point. I gave all these values. If the PLL gets locked to these variables in a steady state, then these variables should not change now because I have already given the variable, right? So I can do this experiment, and I will keep on increasing this delta omega to some value till the time I reach 70 delta omega 1, and I notice if I give 70 point delta omega 1, I calculate all these values, right? And I give these values, and whether the PLL, the thing which we need to check is whether the PLL remains in lock or not. Whether the PLL remains in lock, what it means is all these state variables should remain there, or even if they change somewhat, but finally they should settle to this value only. How is it this experiment is different from the experiment which we were doing before by giving small values, right? Small values also we were actually specifying the exact value and just allowing a very small disturbance to take care of in the feedback. Okay, so this way also you can directly check for the holding range of the PLL. You do not have to give a small step and wait for a long time. Okay, this should not be confused with the fact that if I am using a VCO and I say I give this VC value as, let's say I want something as 0.7 volt in a steady state. Okay, so I give this 0.7 volt and have my FS here, and I let the loop operate. This should not be done in this manner. Let me show you. I said, okay, anyways I have to give VC, so I will give 0.7 volt here. Okay, these two are two different things. In the second case, this 0.7 volt is not the part of the PLL loop, it's an offset. Okay? In this case, it is a part of the PLL loop. Whether this 0.7 is a stable voltage for the PLL, the loop will decide. The loop may wiggle at that point and settle at 0.7. But in this case, this is equivalent to just changing the free running frequency of the VCO. Okay? So do not confuse with, do not confuse with this test bench with this one. Okay? Any questions?
So,